Okay, so today we're going to talk about rotational motion. This video session is about rotational motion. We're going to talk about basically, um, we're going to study the motion of objects and then their acceleration or angular velocity, tangential velocity, RPMs. We're going to talk about all sorts of different ways that these are all affected in ways that different velocities and different forces factor in to affecting quantities of rotational motion. So the first general thing we're going to talk about is a lot of pre-calculus you'll see in this, and some of this you'll learn later on. We're going to talk about radians, degrees, and conversions, and there's a few different formulas actually that the AP Physics 1 formula sheet does not offer for rotational motion. So we're going to go through some extra stuff because this is mostly directed towards AP Physics 1, but you could actually look at this for regular physics or honors physics because it's pretty much a brief intro to rotational motion. It's part 1 of rotational motion. So we're going to look at basically we're going to start with radians and degrees and then converting between the two. So we have radians, we're going to convert to degrees. So we're given radians, and may be written as rad, that's usually how we write it for short. If we're given radians, we could divide by pi to cancel the radians and multiply by 180 to notice that I get degrees using dimensional analysis. Now conversely, vice versa, I could also have degrees and convert that to radians, or whatever it may be. Just happen to put 180, but this could be degrees of any sort, right? Degrees. And then I'm going to multiply. I'm going to be left with pi in this case because now degrees cancel out. And so I'm just going to do pi over 180 over pi. And so very cool, very interestingly enough, we're going to notice that when we look at the unit circle, which is really, really, really going to help us with this. If you look at the unit circle, we notice that each revolution, right, is 2 pi. It starts off from 0. Each revolution is 2 pi, which means that half a revolution is pi, where 180 degrees lies, and 360 degrees lies at 2 pi, right? And then we got 270 degrees out here, right? And then we got 3 pi over 4. We got 3/4 pi. And then up here we got pi over 2, or half pi, which is really just 90 degrees. Okay, so we look at this unit circle here, we could split this up, and we could take a peek at it and just notice that this relationship is really involving the unit circle, converting radians to degrees. Okay, so we have a problem that's asking us how many radians are subtended in an arc. And for instance, we're going to look at one of the AP Physics problem packet problems in the PSI Physics. Like we have one that says how many radians are subtended in a 0.1 meter arc with a circle radius of 0.4 meters. Okay, so basically the concept I'm trying to get out here, I'm not worrying about the numbers. I'm just going to teach about the concept right now. Is that we're looking at an arc, right? That's comprised within a circle, right? So we have this whole circle that's going around. I probably should have drew this in a different spot, but we have this whole circle, okay? And we have a radius, and an S is our arc, okay? And then here is theta in between, right? And now, if you look at this, it actually kind of relates to Pythagorean theorem, because the more I increase this theta, actually R doesn't change, but S will change, right? The opposite side changes, while R's will stay the same all throughout the circle. So what we're going to see here is that we can actually generate some smaller formulas or smaller equations here. So one of the first equations we'll write is theta is equal to S over R, S divided by R, right? Which means that theta also has to be equal to 2 pi times the radius over the radius. Those two cancel, right? And we'll wind up with 2 pi radians, or 2 pi rad, however you want to write it. Okay? And then we notice that they cancel vice versa. Okay, so basically we're basically seeing here that S over R is equal to theta, right? So if we're given an angle, we could solve for our arc, or we could solve for our radius in this case. Okay, so basically, and then based on what information we're given. Okay, and so we also see that we have 2 pi S, or basically you could rewrite this as 2 pi R over S. Okay. Exactly. And so we're going to see what this first problem is. Actually, we're going to actually use that. We're going to use 2 pi r over s, because we're given a 0.1 subtended arc. So this is 0.1 meters, this arc, right? And the radius is 0.4. Okay, so radius is 0.4. I always write my givens down first, everybody, because it's the easiest thing to understand. And then that's my arc. And they're both measured in meters, which is lovely. Okay? So we have this all written out. Now what we see here is that when we plug everything in, we're just going to plug 2 pi times the radius of 0.4 over 0.1, and I'm going to wind up getting 0.25 rad. which is lovely. So I get 0.25 rad, and that's my answer for that, okay? Now I'm asked, what are the degrees subtended in this 0.1 meter arc, right, with the 4.4 meter diameter, okay, or radius, I mean. Okay, we want to know the degrees. Well, if I'm given rad, radians, I can convert the degrees by simply multiplying. I'm going to actually write this up here. I can simply take my 0.25 rad, right, and I can divide by pi, multiply by 180 degrees. Therefore, the radians cancel. I'm left with degrees. And I wind up getting 14 degrees, okay? Or percent. Oops. 14 degrees, okay? So, this happens a lot. Sorry. We get 14%, okay? Or degrees. So what we see here now is, when we go through this, we're going to see different things. Now we're going to get into angular velocity, okay? So we'll absorb that for a minute. And now we're going to get into angular velocity. So when I look at angular velocity, it's a little bit different. I have a little bit more formulas coming into play here when I come into angular velocity. Okay? So angular velocity is written, everything always is written differently. Angular velocity is written as like a W, kind of with a curve to it. You can kind of write it like that. Okay? So angular velocity, the formula for angular velocity, the most common one we're going to see is basically this W is equal to 2 pi over the period. Okay, if we're given period, we could solve for that. But that's only if we're given period. We also have another one where we have W is equal to our change in our angle, our change in theta, right, over our change in time, right? And that kind of makes sense because if our angle's changing, therefore, it's obviously it's going to change over a period of time, right? And our angular velocity is going to change because we have this circle out here, right? And if my angle, my theta between these two lines is increasing, that means that this is increasing, it's moving, it has a velocity, right? So that's another equation we have, okay? We also could come up with, we could also generate another equation, which is lovely. We could generate the fact that we have theta over t. We could generate angular acceleration, okay? So this is angular velocity. We could generate angular acceleration, okay? And that's written as alpha, that's the alpha symbol. Alpha, most people write it as, it's our change in our angular velocity over our change in time. And that's going to be very helpful when we come time to later. We're going to see that our change in our angular velocity over time is clearly our acceleration here, our angular acceleration, okay? So RPMs and velocity change over a period of time, or velocity vary, okay? So it's tangential and RPMs. They're completely different things. We have rotational velocity and we have tangential velocity, okay? So the way I like to look at this is something, usually the best way I think of looking at it is looking at something like a merry-go-round, or even, that's a little more hard to picture because it moves so slow, but even if you're picturing something more like a wheel on a car, or basically anything that spins, you'll see that it spins slower on the inside and it often spins faster on the outside. And we do see that. You grab somebody's arms and you swing them around, right? You notice that you actually spin slower. The person out there is really moving, really ripping, right? And so that's what we happen to see here. So anything that moves, even if you look at a ceiling fan, you'll notice that the inside spins much slower than the outside. And it's true, the speed, the velocity is actually greater on the outside. And there's a reason because of that. So we have our tangential and we have a rotational. So we have our tangential and we have a rotational, okay, velocity for each. Okay, our tangential, basically what we're seeing with tangential is we're basically relating how it is to our radius, okay? So how far away it is. So something closer, an object here at point A is going to spin much slower than an object at point B, and it's very true, right? Whereas both objects, though, A and B, also wind up at the same spot at any given time. So they both have the same RPM. So both have 1 revolution per minute. Let's say that's the rate they're spinning at. If they have 25.7 rotations per minute, they will both have 25.7 rotations per minute, whatever it may be. However, with tangential velocity, though, A is spinning slower than B is, and it makes sense because B has a greater distance to travel. Look at the distance B has to travel compared to A, right? And that's where our circumference formula comes in. Our 2 pi over our radius, right, is equal to our circumference, okay? So the one with the greater radius is going to be inversely proportional to circumference, right? They're inversely proportional to one another. So what that means, with that being said here is that because they're inversely proportional, if I increase my radius, my circumference is also going to increase. Or they're both, I'm sorry, my circumference will change, but rather my velocity. I'm not even going to use circumference. I'm going to say radius is inversely proportional to velocity, and that's a very true statement. So B is going to spin much faster than A because it has a greater distance to overcome, 2 pi over my radius. Or did I say over radius? I meant 2 pi r. 2 pi r is my circumference. So because my radius is directly proportional to my circumference, which makes perfect sense, circumference increases with radius, velocity is going to decrease with radius. And it makes sense because the smaller the radius, right, the smaller my velocity, right? The greater my radius, the greater my velocity. So the further the distance is away, the object has to move quicker to keep up with the object in the inside, which makes perfect sense. Okay, so A has to keep up with B, so B has to move faster at a greater velocity to stay in line with A, because it has a greater distance to travel than A does, right? Because we know velocity, we know that speed or velocity is equal to our distance, or change in our distance over our change in time. So we see that our change in our distance over our change in time must clearly be a factor of having a greater distance will make us have a greater velocity to travel, okay? So they're directly proportional, okay? So these two are also proportional, velocity and distance, okay? So we're seeing that here with tangential and rotational velocity. And so that's the fact that we're trying to get across here, is that velocity is really overall equal to our radius. We could also say that our velocity is equal to our radius times our angular acceleration, which is lovely because of that factor, because of the fact that we have tangential. Even though our RPMs are the same, one is spinning faster than the other, and it is very, very highly true in this case. So we're seeing that the ball is rotating at 2